now the first example that we use where we apply Ampere's law to find the magnetic field is an example that we actually know the answer to, at least partially, which is an infinite straight wire, or just roughly speaking, generally speaking, what we use for short, we say a long wire. Now, what we know about this wire, if I have a long wire, then we know that the magnetic field lines of this wire are actually concentric circles. I'm showing some of them. Circles centered at the wire. And so, for example, you have a circle here, you have another circle here, and a third circle, and so on. So these circles, this is the wire, and these circles are just rings here. But so this is a three-dimensional image, okay, and so on. And when this wire is infinite, and there is no other source of the magnetic field in the surrounding, then the magnetic field in the area around the wire is generated only by the wire. And for this reason, from the symmetry, we can know, it is a fact that we have proven actually by Biot-Savart law. We have found what is the magnetic field of a wire, a long wire, using Biot-Savart law, and we found that it depends only on the distance, okay? But even if you don't know this, symmetry can tell us that the because of the current that is piercing here is flowing, it's uniform and flowing from minus infinity to plus infinity theoretically, okay? Then at any point, when you go around a circle centered at the wire, you see the same environment, and therefore the magnitude of the magnetic field must be the same when you are at the same distance from the wire and on a circle on the wire. And this, of course, explains that you can take as the magnetic field lines lines of this form. The Biot-Savart law tells you what is the direction of these lines. So these are the arrows on these lines, and so on. So what we know from symmetry is that when you have a long wire with a uniform current passing through it, then the magnetic field at some distances, magnetic field lines, are circles centered at the wire, and so the magnetic field is constant on each of these circles, okay? And we know also what is the direction of the arrows on the magnetic field lines, which is by the right-hand rule. We let our thumb go along the direction of the current, and our right-hand fingers, in this case, will curl in the same direction, in the direction of the arrows on the magnetic field lines. And of course, we have infinitely many of these. They are, packed. They are covering the whole wire, and they extend. They have different radii, and they go into infinity. The separation between them drops as we go away. This is just what we have said when we discussed this topic. Now, what we will do here, what we will do for the purpose of applying Ampere's law, is that we will consider this wire, and we say that this carries a current I in this case, and this current is uniformly distributed over its cross section, okay? We want to utilize Ampere's law to find the magnetic field inside and outside this current, okay? Carrying wire. Now, what we know from what we have said here, let's start with outside. And let me take as a cross section, this is my wire, and this is I passing it, okay? This is a cross section of the wire, okay? Now, from my knowledge of the magnetic field of the wire that I have just discussed here, I know the following fact. Now I'm requested to find the magnetic field at a distance r from the center of the wire. Now, I know that the magnetic field lines are concentric circles, and that a circle, there will be a circle passing through this point with the magnetic field, in this case, lines being in this direction. So the arrow will be in this direction. So that's how it will go. I know this. And the importance of this is that if I choose, for the purpose of applying Ampere's law, if I choose this magnetic field line itself as my contour, then the magnetic field is uniform at all points on this contour and is tangential to that contour. So let me draw, this is my contour. And so in Ampere's law, this is my C. Okay? So I choose this as my C. Now it coincides with magnetic field lines in this case, which are concentric circles. Now the direction of the magnetic field at each point, due to the right-hand rule, look, this is the direction of the current. The direction of the magnetic field lines is tangential, and it is in this direction. So for example, at this point, I know this is B. At this point, this is B. At this point, this is B. At this point, this is B. So the magnetic field direction varies at different points, but it has the same magnitude. This is what I know about the magnetic field of this current carrying straight wire. Now, what remains is to choose my DLs, to show what will be my DL, and so to see what's the relation, what's the angle between B and DL, and so on. Now, it will be wise, of course, in this case, to choose my DL to be parallel to B, to take it tangent, because DL is what? DL is an element of arc in this case. But because it's very small, it is a straight line. So if you choose it here, in this direction, in other words, if you choose to traverse the contour in this direction, along the magnetic field lines, then in this case, DL and B will be parallel all over the contour. And so B dot DL in this case will reduce to what? Just BDL, because the angle between them is 0 all the time. Okay? Add to that B is uniform over the whole contour, and so for this choice of contour, this quantity reduces to BDL, and B is uniform, so you take it outside the integral and it reduces to be the integral over the contour. But what is this contour? It is a circle of radius r. So what is this? This is just the circumference of that circle. So this is equal b2 pi r. So this is the left-hand side. And this is what I got, what I wanted. I took b outside, which I still don't know. Now, what is this equal to? According to Ampere's law, it's equal mu 0 I net. I net is the net current piercing the area defined by the contour. Now, what is this area? It is this whole area. And what is the current in this area? It's just I. Positive or negative, apply the right-hand rule of Ampere's law. My right-hand fingers curl with the direction I choose to traverse the contour. My thumb gives you the positive direction, so it's out of the page. What is I? I is coming out of the page, so I is positive. So it's equal mu 0 net, so this is equal mu 0 I. And therefore, I get the left-hand side, b2 pi r is equal mu naught I, and from which you get b equals mu naught I over 2 pi r, and the direction of b is already, I know it. And this is exactly the same expression that we get from the Biot-Savart. Of course, you will tell me that, oh, already we know this. That's true, but let's try to see how we can apply this to the case to inside the current. That is, to find the magnetic field inside the current, at points inside the current. the wire, sorry, okay? So within the current, okay? This is look like, you remember when we found the electric field inside a solid sphere of charge, okay? So this is something similar to that, okay? So let's find it, let's try to apply Ampere's law to that portion. So in this case, for this purpose, what we do is, this is the cross-section of the wire, and this is the center. I want to find the magnetic field inside it at a distance r from its center. Again, the current, there is a current I, which is uniformly distributed over the surface of the cross-section of the wire. This is piercing the wire. Keep this in mind. Okay, now I will repeat the same algorithm. First, look at the symmetry and tell me what should be the contour that I'm using. Now, due to the symmetry also, because the wire is uniformly distributed over the whole area, if you consider a circle centered at the axis of the wire, then from symmetry alone, because you see the same current environment over all the points on a circle, the magnetic field, the magnitude of the magnetic field can only be constant on all points in this circle. Also, from the symmetry, okay, and from applying Biot-Savart law mentally, Biot-Savart arguments mentally, that magnetic field can also be only tangential, okay? So, therefore, again, I choose a circle passing through the point here that I want to find the magnetic field at as a circle, and this is my contour. This is a virtual contour. This is a virtual contour in this case. It's not a real thing, okay? Just like Gaussian surface, it's not a real thing. It's just virtual surface. And the magnetic field lines in this case, if this coincides with the magnetic field lines, then the magnetic field lines again will be, let me assume that they are in the pointing in the clockwise direction. So the magnetic field at these points, which I assumed, I knew now that it is uniform, I assume it to be in this direction again. So once you choose this, now the rest is easy, okay? I want to calculate this integral. So I have to choose my DLs. Evidently, the wise decision will be here again to take the DLs parallel to the field, okay? So that the angle between them 0. Well, if you say I want to take them anti-parallel to the field in the opposite direction, that's quite fine. You will get a minus sign, but also you will get minus sign for the wire, for the current, and so the result will be the same, okay? So there was no worry about did I make the right choice of traversing the contour or not. There is no problem with that. But here, take the DL in this direction also, and so this quantity B dot DL reduces to B integral over DL for the same reason. And this is equal to the right-hand side, which is mu 0 I net. Now, here we have just to be careful in calculating what is I net, because what is I net? I net is the current piercing the area defined by the contour, not by the border of the wire. Okay? So I passes the whole wire. So I passes the whole distributed over the cross section of the whole wire, but I am taking a portion of the wire. Okay? So I net is the current passing this area only. Okay? And what is this? Well, I net here is actually, well, first of all, it's positive because, it's coming out, and the problem is saying it's coming out of the page, and because I traverse the contour in this direction, my thumb is pointing outwards. So I net in this, so this is the positive direction. I net will be what? Will be the current density multiplied by the area of what? This area. The area defined by the contour. And what is this? This is the area of a circle of radius r. So it is J multiplied by pi r squared. But what is J? The current density. I am assuming, I am given in the problem that the current is uniformly distributed over the cross section of the wire. And so this is just I, the current density, is just I divided by pi r square. What is r? R is the radius of the wire itself, where the current is distributed over. Okay, so I over pi r square multiplied by pi r square. Now these cancel, and so you get, it becomes I over r square multiplied by r square. Okay, so this is my I net in this case. And so I just substitute it here. So I get, I work it out here. So this is equal mu naught I r square over r square. Now I substitute for this. This is equal b multiplied by 2 pi r equal mu naught I r square over r square. This is a square here. Okay. Now this r cancels this, and b in this case will be equal mu naught over 2 pi r square I multiplied by r. So as you can see, it grows now linearly with r. So the magnetic field inside the wire grows linearly with r. Whereas the magnetic field outside the wire, you remember what it was? It was mu naught I over 2 pi r. So it was falling with exponentially. So if you plot it, and this is r, and this is b, okay, and this is just the radius, then it increases until this point here, and then it decreases exponentially. Now this value here, which is equal the value of the magnetic field at the surface, this is equal, in our case, mu naught I over 2 pi r. This is mu naught I over 2 pi r. Now you get the same result whether you calculate it from here, from inside, or you calculate it from outside. Okay, because here in this region, b equals mu naught I over 2 pi r square r, and here b is equal mu naught I over 2 pi r. So substituting r equals to capital R from this side or from this side, you get always this same value here from both sides. Okay, so this is the behavior of the magnetic field of a current inside and outside a long wire, where the current is uniformly distributed over the area of the wire. Now this is the simplest application of Ampere's law to find the magnetic field of given current distribution when that current distribution has a high degree of symmetry. There is a couple more examples that we will be considering now eventually, which are the magnetic field of inside an infinite solenoid, or what we call an ideal solenoid, and also the magnetic field inside a toroid. Okay.